Hello, organic chemistry students. This week's lab activity will just be working through a worksheet. And while I will go through some of the answers, definitely submit the whole thing filled out. Just, because that's how I'm going to grade it. For this worksheet, there is infrared spectroscopy and NMR nuclear magnetic resonance spectroscopy. First one, IR spectroscopy. It's very useful for determining the presence of certain functional groups or certain types of bonds in your molecule. For example, if you have, say, a carboxylic acid functional group or a carbonyl C double bond O or C single bond O, C bonded to a chlorine atom, things like that, that's what IR will tell you. It will not be able to tell you the identity of a molecule if you don't already know it, but it can be used to determine what kind of bonds and functional groups are in your molecule. So for this first page, there are 4 molecules to look at. And when it comes to IR, simply let's just start with determining what kind of functional groups are present in our molecules. So molecule number A, well, what stands out is that there is an OH alcohol group. So something that would show up as an O bond hydrogen stretch. IR, it's looking at the stretches of the bonds that are present. Molecule B has a carbonyl, a C double bonded to oxygen. And also what will be important later is the presence of that aldehyde hydrogen, that carbon bonded to hydrogen in a aldehyde. A very similar molecule, molecule C, or should I say a very similar functional group, is the ketone carbonyl. That's still a C double bond O, like in the case of an aldehyde. And then molecule D, well, molecule D has a carbon bond to an oxygen, which is something that would show up for these first 3 as well. But what's unique is that it's only a carbon single bonded to oxygen. You would not see a carbon double bonded to oxygen, so you would not see the carbonyl stretch, and you would not see the OH alcohol stretch as well. And well, when it comes to determining when it comes to linking each molecule to its respective IR spectra, well, really it's just start with the functional groups that you have, and then the web link that is in the experiment 4 folder on Blackboard. There is an IR web link to a table of a great variety of IR values. So you can go to that web link and say Control F, search for, say, alcohol or OH, and it will show you where those normally appear on an IR, or you can search carbonyl, ketone, aldehyde to quickly go through all their numbers. And here's essentially how to start solving this page. Let's take, well, in only one of these molecules, is an OH functional group actually present. And the nice thing about alcohols is that they tend to show up at around 3,000 wave numbers, and where essentially this region right here would be more toward 3,000, whereas the region, or should I say, the region on the left side of a IR spectra is more toward the 3,000 wave numbers, whereas as you get closer to the right, you're actually looking more toward 500 inverse centimeters or wave numbers. And an OH alcohol, an alcohol group, just like or very similar to a carboxylic acid functional group, these are the only 2 that will show up as a very broad peak, or on IR they look like valleys. Alcohol will show up as a very broad peak on the IR, and well, the only spectra that shows a very broad peak around 3,000 nanometers, where a alcohol peak will show up, is actually in the bottom left spectra, and essentially this guy right here, that would be the OH stretch. It looks like if you were to flip it over, it looks like a pretty broad mountain. If that peak was so much shorter and much more broad, then that would imply a carboxylic acid. But with a broad peak that's pretty deep in the left corner of a spectra, that's where an OH stretch would show up if there's an OH alcohol group in your molecule. So right from that automatically says that this bottom left spectra belongs to molecule A. That's the only molecule that has an alcohol group. Now, when it comes to ketones and aldehydes, that C double bond O, that will show up around 1700 on the IR, around 1700. So effectively, let's look for a very narrow, very steep peak around 1700. And while it will be more clear to see the numbers on the worksheet in front of you, I'm just going to refer to what I know. Essentially 1700, though the numbers are small on the screen, that is essentially around the middle. So this peak this IR spectra in the top right has a sharp peak around 1700, and also the bottom right spectra also has a peak that's very narrow and very deep around 1700. So therefore, these two are both indicative of a C double bond O in the molecule. Now, that leads to one problem, and that is, well, molecule B and molecule C, they both have carbonyls, or yes, they both have C double bond O's. Therefore, which spectra belongs to B and which spectra belongs to molecule C? Well, what should be emphasized is actually that aldehyde hydrogen, or effectively this guy right here. This aldehyde hydrogen, that carbon bonded to a hydrogen, an aldehyde hydrogen will show up as its own peak as well. And that shows up more around 2800 and 2700. And effectively, it's going to be this little corner right here, this little separate guy right there. This peak infers that there is an aldehyde hydrogen, a C bonded to a hydrogen as part of an aldehyde group, ALD. Therefore, taking those two bits of information, where there is a carbonyl stretch in the center around 1700 and an aldehyde hydrogen stretch around 2800 or 2700, this implies that the bottom right spectra belongs to molecule B. And well, the top right, therefore, would have to belong to molecule C, because that is the only spectra that has a steep peak around 1700, indicating the presence of a carbonyl group. But also there isn't that separate little peak off by this guy right here. There isn't that separate little corner that would imply that there is a aldehyde hydrogen. Therefore, since there is no additional peak right around here, off to the corner of this larger guy, that means that you're just looking at a ketone and not an aldehyde. And then, by default, the top left would then be D, because even though it has a C bond O, which generally shows up around 1200, somewhere in this region, not really relevant. What's relevant is that there's no C double bond O stretch and there's no alcohol mountain. And that therefore shows that that top left is not any of the alcohol or any of the carbonyl molecules. And that's how that works. Page 2 is going to be very similar. Essentially, you have various molecules, some that have carbonyls. This one in the case is an aldehyde. This one also has a carbonyl stretch that is part of an ester, methyl ester. Here you have a carbonyl that is somewhat in conjugation with that double bond. A double bond will also show up as its own peak, which you can look up on the peak table. And here we have just a carbon bound to oxygen. And also there is an aromatic benzene ring, which can show up on the IR. So similar to the first page, just look at the certain functional groups that you have to work with and use that to start piecing together which IR spectra in the bottom belongs to which molecule. And a nice little hint is that these three guys, if you do actually try to look for a benzene series of peaks, well then the guy in the bottom right would be the only one that does not have a benzene, because it does not have a 6-sided ring where each carbon has a double bond. But really, try not to focus on the benzene ring. That's more for if you want to try to get into the very niche interpretation of IR. For the second page, just for the top, start identifying functional groups and start saying where you would expect to see stretches for those particular groups, like based off of the IR table link in Blackboard, you would be able to look up that a C double bond O should be around 1700. A aldehyde hydrogen, in the case of the top left molecule, cinnamaldehyde, would show up either around as a little corner around 2900. Sometimes it shows up as a little doublet peak, things like that. And just essentially list what kind of bonds and what wave numbers you would see them around, and then start trying to identify the bottom spectra to either of these 4 molecules. And well, that is basically the core of IR. The rest of this worksheet will be getting into nuclear magnetic resonance spectroscopy, which is very straightforward. And while it's going to go off the screen, essentially there is an image I have on Blackboard which gives a very we'll get into that. Basically, nuclear magnetic resonance spectroscopy. There are many different types of NMR, some that will only give you information on the different kinds of carbon environments, some that will tell you the different kinds of fluorine environments. The one most common and very effective is proton NMR, which is what you're looking at. These spectra all belong to proton NMR, where it is analyzing the different environments of hydrogen. And just as an example, for the first guy, essentially just to start out with, a good rule of thumb is to start drawing in the hydrogen present in your molecule. So, for example, we have a carbon right around here that is bonded to a bromine and bonded to a benzene ring. Well, carbon likes to bond 4 times. Therefore, that implies that the 2 bonds that are not being shown are 2 hydrogen. So I'm just going to draw those guys in right here. Now then, on the benzene ring, each carbon of the benzene ring, or I should say most carbons on the benzene ring have 3 bonds that are being shown, where essentially, take this carbon for example, it is double bonded to 1 carbon and then single bonded to another carbon. Well, a double bond and a single bond, that adds up to 3. Therefore, there's one bond not being shown, and that is going off to a hydrogen. And that'll be similar for most of the other carbons as well, where these other carbons are single bonded to just one hydrogen atom, or just one hydrogen. And just to make sure you do not get tripped up, because it happened with my students at Wilkes, I will point out that this carbon right here in purple, that carbon is double bonded to the topmost carbon, is single bonded to the carbon right below it, and is single bonded to the carbon that has 2 hydrogen attached. Therefore, that carbon in purple, part of the benzene ring, is already bonded 4 times. Therefore, there is no hydrogen attached to that particular carbon. Now then, with all the hydrogen spelled out or visible, for NMR, here's essentially what is done. You just start labeling the different unique environments of hydrogen. And if there's symmetry, then, well, we'll get into an example of symmetry. Let's take, for example, these 2 hydrogen right here. These hydrogen, let's just label that, say, A, and then let's take the hydrogen on the ring. We'll label all these guys as, say, B. That's essentially the first or the second step of filling out an NMR, showing the different hydrogen environments and then labeling each unique environment based off of symmetry. And now then, there is a generic NMR peak, or there is a diagram on Blackboard Learn that basically shows various regions where certain hydrogen environments will show up, such as take a hydrogen environment that is just a plain Jane carbon, like the carbon bonded to 2 hydrogen atoms, the ones labeled A. Those guys will show up right around here. That actual number can vary quite a bit. What is actually very consistent is the hydrogen coming off of an aromatic benzene ring. They like to show up around 7 parts per million, 8 parts per million, things like that, around this region right here. Therefore, this peak is actually going to be the hydrogen of the aromatic ring. Therefore, the last step of essentially filling out an NMR spectra is just correlating the labels you put on each unique hydrogen environment in your structure to the peaks that are present on the NMR. So the carbon that is bound to bromine and bound to the ring, that carbon which has 2 hydrogen attached, that's one unique environment, and that was labeled and that was correlated to the rightmost or most upfield peak on the NMR. And, well, I labeled that carbon A, therefore I'll label that peak on the NMR spectra also A. And then the hydrogen on the ring, well, they got labeled overall, they got labeled B, therefore the peak around 7 to 8 parts per million, 7 to 8 ppm, that will also be labeled B on the spectra. Now, there is something that we didn't really get into in this first spectra, but there is something called the N+1 rule when it comes to NMR. And essentially, the N+1 rule will tell you it will tell you how many times a particular environment will break off into sub-peaks. And the rule is basically the number of neighboring hydrogens plus 1. So let's start filling out the various hydrogen in this molecule. This molecule right here, the bottom molecule, the rightmost carbon, is a methyl group. So essentially this is a CH3. So I'm just going to spell out those 3 hydrogen right there, just because it's small on this screen. And then the carbon directly to the right of it, well, that carbon is bound to 1 carbon and a second carbon, and only single bonded to those 2 carbons. Therefore, 2 single bonds adds up to 2 bonds. There are 2 hydrogen that are currently not being shown, and now they are. And then all the way on the left is another methyl group, so that carbon also has 3 hydrogen that are bound to it. In this case, the carbonyl, the C double bond oxygen, that carbon does not have any hydrogen, therefore it will not show up. The hydrogen will not show up for that carbon because there are no hydrogen attached to that carbon. Now then, essentially we have a molecule where the rightmost carbon is bound to 3 hydrogen, the leftmost hydrogen is bound to 3 hydrogen, or the leftmost carbon is bound to 3 hydrogen, and the second carbon from the right is bound to 2 hydrogen. Here's how the N+1 rule works. Let's just say I want to label this methyl group, these 3 hydrogen right here on this rightmost carbon, I'm going to label that A. Now, the hydrogen on that carbon, the neighboring carbon has only 2 hydrogen on it. And effectively, I'm looking at this carbon, these hydrogen right here. The neighboring carbon only has 2 hydrogen, therefore 2 plus 1 would be 3. The signal from these 3 hydrogens would get split 3 times and would essentially form a triplet. Now, the next carbon over, essentially this guy right over here, is attached to 2 hydrogen, and it is neighboring 2 more carbons. And by neighboring, I mean the carbon is bound to 2 other carbons. For this particular, for the carbon that these hydrogens are attached to, the carbon to the right of it has 3 hydrogen, and the carbon to the left of it has 0 hydrogen. Therefore, 3 plus 0 would be 3. Neighboring hydrogen, and we're going to add 1 more. Essentially, that adds up to 4, or that signal for those 2 hydrogen would split up as a quartet. And I'm just going to label those 2 hydrogen as B. Now the last hydrogen environment would be the hydrogen all the way on the left, those 3 hydrogen. Those 3 hydrogen on the left are bound to a carbon that only has 1 neighboring carbon, the carbonyl carbon. And that neighboring carbon has 0 hydrogen attached. Therefore, 0 plus 1 would be 1. The signal for these 3 hydrogen will come up as a singlet. And I'm just going to label that as C. Now then, we essentially have our 3 different environments for protons are 3 different proton environments, all labeled either A, B, or C, and based off of the neighboring number of hydrogen plus 1, we know that the signal that corresponds to environment A, that will break off into a triplet. The signal for environment B will break off into a quartet, and the signal for environment C will break off into a singlet. Quartet, triplet, singlet, that does not mean the number of hydrogen for that signal. That means the number of hydrogen neighboring the ones that you are actually looking at. So essentially, environment A will show up as a triplet. Well, the only signal that shows up as that looks like it's split into 3 is actually this guy all the way on the right. So I will label that triplet A to signify that I'm relating it to environment A on my structure. Now, environment B, that has 2 hydrogen, and the signal for those 2 hydrogen is being split into a quartet. And the only thing that looks like it's a quartet would be this guy all the way on the left. Therefore, I'm going to label that peak as B. And then finally, environment C. Well, environment C, those 3 hydrogen are bound to a carbon that has no neighboring carbon with hydrogen attached. Therefore, 0 plus 1 adds up to 1. That will show up as a singlet. This very tall peak is a singlet. Therefore, that will get labeled as C. And that will be how to essentially solve that guy right there. Really, it's more or less writing in what hydrogen you actually have, whether a carbon has 3 hydrogen or 2 hydrogen or whatever, and then determining how many neighboring hydrogen are there to the carbon that you're on, and then add plus 1. That will tell you if you're going to break off into, say, a doublet, triplet, singlet, things like that. And, well, another example. So the top example and the bottom example, they're very good for looking at, say, symmetry. And let's just fill in those hydrogen. Well, the ring itself, each carbon that is triple bound, or, well, that only has a double bond and a single bond to neighboring carbons, they each still have 1 hydrogen that is not being shown. And then the other 2 carbons in this molecule are bound to a chlorine atom and to the ring. Therefore, they each have 2 hydrogen that are not being shown. And then as for these carbon that I'll draw in orange, well, they actually have no hydrogen attached. Therefore, they're not going to show up, or the hydrogen for those carbon are not going to show up because there are none. Now, when it comes to the symmetry of a molecule, if 2 proton environments are the same based off of symmetry, then you would label them the same. For example, take the hydrogen, the protons that are connected to a carbon that is bound to the chlorine atom and to the ring. Well, based off of symmetry, these hydrogen on the right and these hydrogen on the left, they are effectively the same. They would their signals would show up in the same spot on an NMR. And then the hydrogen on the ring itself, well, they would also show up as one particular signal. Therefore, the 4 hydrogen on the ring, I'm just going to label that B. And well, hydrogen on a ring, on a benzene ring, they like to show up around 7 to 8 parts per million. Therefore, this single peak is for the 4 hydrogen in this ring. Now get labeled B based off of how I determined to label it in the structure. And then the only peak left over, well, that would be for the hydrogen environments labeled A. Groovy. Now, for the current examples shown, the hydrogen on that benzene ring have more or less all coalesced into one single peak. There will be examples where that is not necessarily true. For example, the bottom guy right here. Now, the bottom guy essentially is a benzene ring where 2 of these substituents are methyl groups. So, effectively, this guy right here and this guy right here each have 3 hydrogen. And, well, I'm just going to label those guys environments A, because based off of symmetry, they're the exact same thing. Now then, filling in the hydrogen on the ring itself, there's a carbon here that only has 4 bonds currently being shown. Therefore, there's a invisible hydrogen bond that was not being shown. And similar to the 3 other carbons as well. So those are the 4 hydrogen on the ring itself. Well, let's start labeling those guys. Effectively, let's say this hydrogen right here that is between the 2 carbons that each have a methyl group coming off of it. Let's label that A, because based off of symmetry, it's the only one that is between both methyl groups. So it might show up somewhat, based off of symmetry, it would get its own label. And then the other carbons that are adjacent to the carbons with methyl groups, each of those carbons have a single hydrogen that, based off of symmetry, are effectively the same thing. So I'll label each of those B. And then the final carbon, the one furthest away from environment A, that one can get its own label based off of symmetry as a unique hydrogen environment. Now then, essentially, what is being shown here? And actually, I wrote A more than once. So actually, I'm going to cross out this guy right here and label that D. My bad. There we go. Now then, we essentially had the methyl groups, their hydrogen labeled A, and then the 3 different hydrogen environments labeled B, C, and D, the ones on the ring. So, on paper, based off of symmetry, there are 4 unique hydrogen environments. However, on the actual spectra, there are only 3 main peaks, which would be the main peak right here, the main peak a little bit upfield of 7, that means around, say, 6.9, 6.8 ppm, and then the peak a little bit past 7 ppm, a little bit downfield, maybe 7.1. Those are 3 unique peaks. Therefore, if we have 4 unique hydrogen environments on paper, but there are only 3 peaks, that implies that 2 of them are similar enough that they essentially are overlapping. And you will have examples where you might actually see that later. Well, I'm just going to solve this one just to show what happens if you infer that two of those hydrogen environments in the structure actually show up in the same place. Well, right from the start, the only thing that's not on the ring, the only hydrogen environments that are not connected to the benzene ring are the methyl groups. Well, or are the hydrogen connected to a carbon that is then connected to the ring. Those methyl group hydrogen, which are labeled A, well, methyl groups, they show up quite upfield, quite far to the right. And there's only one peak to the right. Therefore, we'll label the rightmost peak as environment A to signify the hydrogen of these methyl groups. Now, what can be observed is that essentially we have these two main peaks around 7 parts per million. And 7 to 8 parts per million, those are going to be for hydrogen that are directly connected to a benzene ring. Now, it does appear that one of these is larger than the other, so that could possibly mean that there are more overlapping hydrogen environments. And just to show how you would represent overlapping environments, environments B and C, they're both one carbon away from the carbons that are connected to those methyl groups. So they are the more likely candidates for possible hydrogen environments that are overlapping. So of the two peaks that are around 7 parts per million, the rightmost one, I'll just say, is a combination of environments B and D, which you can write that as B comma D or B plus D. Either one would work. Essentially, you would label that particular group of peaks as B and D in some way, shape, or form. Therefore, the other peak that remains could be labeled as environment C, because that proton, that hydrogen, is connected to a carbon that is furthest away from the carbons connected to methyl groups. Therefore, it would be the most likely one, or well, since it's the only one that is not connected to a carbon that's only one away from the methylated carbons, it would be the most likely candidate to show up by itself instead of overlapping around the other, instead of overlapping with the other proton environments. Now, as far as the rest of the molecules, they're going to more or less follow the n+1 rule, and potentially you might see symmetry where if it's the same exact symmetry, hydrogen environment symmetry, then just give it the same label. In this case, we have on page 5, there are 3 different hydrogen environments. There is the hydrogen connected to that is part of the OH group, so the alcohol hydrogen. There are also 2 hydrogen coming off of the adjacent carbon where the OH is bound to. And then there is also 2 hydrogen connected to the carbon that is chemically bound to the other carbon that we just drew in the hydrogen, as well as to the carbon right here that is triple bound to that nitrogen. Now, when it comes to hydrogen that are not being shown, the only time that there are invisible hydrogen is when they're connected to a carbon. If hydrogen are connected to an oxygen or to a nitrogen, to a sulfur, those would be drawn in. So in this case, the nitrogen all the way on the far right, there are no hydrogen drawn in as bound to that nitrogen. Therefore, there are no hydrogen environments. There are no hydrogen connected to that nitrogen, so it will not show up on the NMR spectra. And well, it looks like you have one peak here, one peak here, and a little peak down here. And I'll just let you know right off the back, I'm assuming that NMR is new to you guys. And I will go off of the assumption that you may not have been taught this stuff yet in the lecture component. Well, an alcohol hydrogen, well, it will like to show up as a tiny broad peak as opposed to very fine straight peaks. So therefore, let's just say labeling the alcohol hydrogen as environment A, labeling the adjacent carbons protons as environment B, and then the very next two protons as environment C. Well, the alcohol hydrogen, it will be this middle peak right here, that little mound. Because effectively, that's how alcoholic protons show up. They have a situation where hydrogen, as part of an alcohol group, they can be exchanged, or they can essentially leave the molecule rather easily. Therefore, that's what causes the peak for the alcohol hydrogen to become more broad, because it can actually leave the molecule more easily and then come back on. Hydrogen that are more stuck to the molecule, wherever they are, they will show up as very straight, very neat peaks on an NMR. And well, there is, let's see. Well, you will more or less be able to use the N+1 rule for most of the other molecules. I will say right here that the hydrogen labeled as B, that hydrogen environment would show up more downfield or more to the left, because they are connected to a carbon that is directly connected to an alcohol. Therefore, being nearby an alcohol, that causes those hydrogen to become more de-shielded. And if something becomes more de-shielded, then the peak for those hydrogen environments gets moved downfield more to left. Whereas the hydrogen connected to environment C, they're further away from the alcohol group. Therefore, they're not going to be as de-shielded. They're going to remain more upfield, more to the right end of the NMR. Now, as far as de-shielding and shielding go, I truly believe that is probably going to be a concept that's more advanced than what Organic Chemistry 1 needs to do. Therefore, this is the only spectra where that would actually really matter. The rest of them, just do your best to do the N+1 rule. And well, in all honesty, look them up. Look up the actual molecules if you need help. I guess I can say that this guy right here, that alcohol, that would show up as this peak right here, because it's a little more broad toward the base as opposed to being nice straight lines. So you can show the hydrogen that are coming off of this carbon, and then the remaining carbon has 3 hydrogen. You can use the N+1 rule to do your best to figure out which of those peaks belong to which hydrogen, and things like that. This worksheet is not meant to be, hey, I assume that you guys are experts. It's meant to be a supplement to lecture. However, I do not know what is being discussed in lecture. Therefore, I will go off the assumption that this is going to be an introduction to you guys. Therefore, I'm not going to be killing you when it comes to grading this assignment. Just at the very most, show me that you're at least putting intelligent thought into determining what each peak belongs to. And well, for the other two molecules on page 6, I will let you know right out the back that essentially the hydrogen here and here are very close to that aldehyde group. Therefore, and the hydrogen connected to the ring here and here are distinctly far away from the aldehyde group. Therefore, this aldehyde group will cause this hydrogen environment and this hydrogen environment to show up separately. So basically, that's why around 7 to 8 parts per million, despite those hydrogen being on a ring, they actually show up as two unique hydrogen environments. So one of these belongs to one of these guys, and the other belongs to, well, the other. And then a aldehyde hydrogen. Aldehydes, they love to show up around 10 parts per million. So the peak around 10 ppm, that is definitely for the aldehyde hydrogen. And because this molecule is really great for signifying a lot of concepts, this carbon right here has one hydrogen that's not being shown, and the two methyl groups here and here, just based off of symmetry, they are, the hydrogen on those carbons would show up as one peak, would show up as the same peak. So just to start deciphering all this, I'm going to label this hydrogen here, I'm going to label as A. The hydrogen here, I'm going to label as B. And based off of symmetry and proximity to that aldehyde group, the other carbon I will label as B as well. These two carbon are going to be labeled C. And then, let's see, the hydrogen coming off of that carbon I will label D. Therefore, the two methyl groups right here the two methyl groups right here and here, those three hydrogen I will label as E, because based off of symmetry, they'll get the same label because they're more or less the same carbon. So, just going to start deciphering all this. Well, A is going to be very easy because environment A, that's the aldehyde hydrogen. Aldehydes, they love to show up around 10 parts per million. So, hey, cool. That guy right there. And then as far as the benzene rings, well, for the hydrogen that are closest to that are attached to carbons that are closest to the aldehyde substituent, that aldehyde substituent is going to cause those hydrogen to become more deshielded or more downfield. So these guys right here are effectively going to be what environment B is. And then environment C, the two hydrogen that are furthest away, So this guy and this guy, those hydrogen are attached to carbons that are 2 away from the carbon attached to the aldehyde group. Therefore, they are going to be less deshielded. They're going to be more upfield. Therefore, that double peak right there would be environment C. Now, the last 2 peaks on the right, they essentially follow the n+1 rule. So let's look at environment D. Environment D is 1 proton, which is connected to 2 other carbons. And those 2 other carbons each have 3 hydrogen. So 3 plus 3 adds up to 6 neighboring hydrogen. 6 plus 1 would be a 7 split, septuplet. Therefore, this guy right here, environment D, would show up as a septuplet or was sometimes called a multiplet. So this guy would show up as a multiplet. And then environment E, well, environment E, which goes for this methyl and the other methyl, they are each 3 hydrogen connected to a carbon. And it doesn't matter how many hydrogen are in that particular environment. The n+1 rule is the number of neighboring hydrogen. Well, each of those carbons, they are bound to 1 carbon in the middle that only has 1 hydrogen. Therefore, 1 plus 1 would equal 2. That would look as a doublet. So the only doublet that can be seen on the NMR spectrum would be this guy right here. Therefore, that is considered one single peak that's split into 2. Therefore, that peak would be environment E, because based off of the n+1 rule, it would show up as a doublet. And then environment D, which would be a multiplet. This may show up better on your personal copy because you'll be able to better zoom in. But that multiplet right there, this multiplet right here, is effectively what environment D is. So, cool. That would be a more complex way of identifying all of those guys. And, geez. Again, assuming that you're not, that you are more or less brand new to this stuff. Let's just take this out. This carboxylic acid has 1 hydrogen. That would show up. Therefore, we have 1 hydrogen right here as 1 unique hydrogen environment. We have hydrogen coming off of the carbons that are closest to this very long substituent. Therefore, based off of symmetry, they would show up as their own environment or their own group of peaks. And then these 3 hydrogen connected to these 3 carbon right here, they are suitably far enough away from the large substituent that has multiple carbonyl bonds that effectively the 3 hydrogen on these 3 carbon would show up as 1 unique peak would show up as an overlap. So you could say label 2 of these carbons as 1 letter and then the bottom carbon as a second letter, or you can use just 1 letter to represent all 3. More or less, whatever you do, you would have that label or those 2 labels for the peak that represents the protons on those 3. And well, similar to alcohols, a proton on an carboxylic acid will show up as a broad peak, where at the base of it, it's very broad. Carboxylic acids, they also like to show up around 10, 11 ppm. And then any hydrogen that are close to that substituent, they will become deshielded. Therefore, they will appear more to the left. So anything connected to the benzene ring will be around 7 to 8 ppm, but the hydrogen and blue that are closest to the large carbonyl and carboxylic acid substituent, while all the hydrogen directly connected to the ring will show up around 7 to 8 to 9 ppm, these guys right here will become more deshielded or will appear more to the left than what the 3 bottom hydrogen will be at. So do your best to label that guy appropriately. And then the last 2 pages involve determining the identity of these 2 molecules, where one molecule is essentially CH3 C3H5ClO2. Therefore, it has 2 oxygen, 1 chlorine. It has 5 hydrogen and 3 carbon. So there are only 3 carbon attached. Therefore, you're not going to have a molecule that has like 4 or has a benzene ring of 6. It only has 3 carbon. And one of the first things that you can use the IR in the top of each page to basically help you determine what kind of groups do you have. Well, you have this guy right here, that's a mountain. Well, if this was more steeper, that would imply an alcohol. This is pretty broad and pretty not very steep. Therefore, that implies a carboxylic acid group somewhere in your molecule. And just as some further confidence, this peak right here implies that there is a C double bond O. Now, these guys right here, the NMR on the bottom, basically use this to determine the actual structure of your molecule based off of the N+1 rule. So however many hydrogen are on the carbon you're looking at, determine how many hydrogen would be nearby. And if you can't really determine, then draw some drafts of a chemical structure and see if they make sense. And well, yeah. Again, not going to grill you guys because I am assuming that this may be new to you. So, in all honesty, do your best. You're more than welcome to say you have a lab partner you want to talk with. You can work together, social distance or whatever, things like that, or work by yourselves. Ask me questions throughout the week. This will be due next week. And then page number 8, same exact thing. There's one molecule. The formula is C5H10O. Therefore, there is a single oxygen. And, well, the IR will tell you if that is an alcohol, if that is a carbonyl, like for a ketone, or maybe an aldehyde, if you see that characteristic aldehyde hydrogen. And then the NMR, well, that'll help you determine the different number of hydrogen environments, and then the N+1 rule. Like, for example, this guy is a singlet, therefore, whatever number of hydrogen are connected to some carbon, those hydrogen are connected to a carbon where the neighboring carbon has no hydrogen attached. Because 0 plus 1 would be a singlet, and this guy right here is a singlet. But whatever. Complex stuff. Lots of so much stuff. So this would be much more appropriate really teaching in person. However, enjoy this by all means. Catch you guys honestly next time I see you. For Monday's section, you will show up to class next Monday. However, you will have a substitute instructor because I will still be in mandated quarantine. As for Thursday's section, the following week, I will be back, so catch you guys in person. And well, yeah, that's it. See you all whenever.